Hi, and welcome back. So before we kind of get back into undergraduate fluids, this is actually the right time. We've already done a bit of Panton with the index notation, but here's sort of the right time to kind of come back and read Panton's 1 through 6. And some of it is it's going to reinforce what we've already kind of talked about with just a little bit more math, because he does write a little bit more at the graduate level. It's also because his doctorate was actually in applied mathematics, if I remember correctly. And really kind of fills in a few blanks that I find necessary when we're talking about fluid mechanics, sort of before we advance sort of the rest of the way into kind of the undergraduate textbook in chapter 6. So really, if you go look at chapter 1 in Panton, good discussion, but the thing I appreciate for the very beginning in chapter 1 is actually the discussion on what's continuum. Okay, so continuum. We often use this loosely. And what he then does is defines really nicely, this is basically log of some distance L, and this will be density. However, density is going to be defined very specifically as, I'll write it right here on the bottom, density being defined as the sum of masses over the volume, forgot to put in there, as the limit of volume goes to 0. And so, because at some point you have a bunch of particles, right? And so depending on this scale L, this is log layer, at some point, effectively you're in the noise of like, it's particles, it's all this stuff. It's not quite accurate to call it continuum mechanics. You can have this happen at, say, like high atmosphere, where the atmosphere is really starting to thin out. And if you have a real hypersonic vehicle or a kind of reentry, it's not quite okay to call it a continuum, right? It's sort of your spacecraft is being hit by sort of random particles. It's not quite there. And then it settles in to a very nice, what we would call the continuum assumption, but then it can start deviating. So easy deviations would be like, if you're talking about the Earth, you're studying oceans, at some point you hit a continent. Like there's a length scale at which that doesn't work anymore. And so all these things would happen if you're talking about almost any flow of interest. At some point, there's sort of this natural boundary, which we usually we'll talk about as a boundary condition, but it's just important to realize that it doesn't go off to infinity. So that's a good discussion there in chapter 1. Make sure you sort of get familiar with that. And the other one is that there also are phase discontinuities. So I'll just write that here as phase. That you could be studying water that is boiling, and you'll have this jump in density from sort of liquid water to vapor, and that's a physical jump, and so it's not necessarily appropriate to call it a continuum. If you really zoom in, you're going to get this sort of very frothy surface that might be too difficult to handle. So just in general, two-phase fluids or multi-phase fluids are very difficult, and this continuum assumption is difficult, and certainly nothing we're talking about here in these 4 books are going to get into what we would consider multi-phase flows. At most in thermodynamics, we would talk about a mixed state where you have both a liquid and a vapor, but we would call it as a system state. We know it's multi-phase exists there, and then we know how to handle the math in terms of the transition. But from a fluid mechanics point of view, we're not going to talk about multi-phase flows. They are hard, by the way. Okay, a very active area of research and really challenging. And by the way, very appropriate for those of you who either work in the oil and gas industry, right? The whole thing is a very difficult multi-phase problem. Okay, chapter 2 is a great review of thermo. I actually appreciate in this edition, he does a really good job going into that. So, this is a great chance to sort of review thermodynamics. It'll be a lot of stuff that we've kind of talked about already in this book club. So great kind of review there. Chapter 3, we've already done for the most part, which was index notation. But I'm going to add one piece here that we hadn't talked about when I covered that section, because we're going to need it. Okay, the first one is actually symmetric and anti-symmetric matrices. Okay, so if you have a matrix, Tij, so the notation that is used in Panton and used elsewhere, sorry, not to imply it's just in this book, but sort of round brackets around your index. So this is a matrix. The round brackets is inferring that this is the symmetric part. So you would take half of Tij and then Tji. And remember, so because of this, it's effectively the transform, right? If you want to go back to your kind of square matrix notation. And so this is what you're going to get is a matrix that's symmetric. And then likewise, the square brackets would refer to a matrix that is completely antisymmetric. So Tij minus Tji. This would be the antisymmetric part. Now, if you add the two of them together, you get back your real matrix. Okay, that's important because we're going to define the strain rate matrix, and I've already kind of used it, but loosely. Here I'm going to be a little more accurate. The strain rate matrix of fluid is going to be the symmetric portion, like that. And so it'll be, if you write that out, it would be 1/2 of del IUJ plus del JUI. Okay, and that's important. And when we're incompressible, and we're actually going to finish here by talking about viscosity. When we're incompressible, you'll see how it kind of simplifies things. But this is actually the strain rate tensor, and it's an important part of what we're doing. Okay. Then chapter 4 is a good conversation. A lot of times, and I'll kind of write it here to not block myself out. So there's the Lagrange formulation of fluid mechanics, where really you're sort of still tracking particles, even though you might be in a continuum framework. This would be, say, along a streamline. We'll actually get into streamlines and things like that. But there's sort of two ways to look at the laws of motion, and that's kind of Lagrangian versus Eulerian, where Eulerian, you might have these flows, but you're sort of looking at it from a control volume point of view. You're letting things pass by. So it's a good read, especially for those in graduate school. You get a bit more familiar with that. In fact, a lot of visualization techniques will come back to actually using sort of this Lagrangian approach for us to understand like streamlines and trying to get an idea of how a flow is being visualized. It's really easier to talk about particles along a track than it is to try and visualize this three-dimensional vector field. It gets pretty complex. So that's a good read there. And then the final piece in chapter 4 that's introduced is the substantial derivative, and that's used as capital D. So if I have some generic A, I'm looking at the substantial derivative of A. That's really just this term that we've already seen a lot, which is the time rate of change of A as a partial derivative plus uj del j of A. And so this is sort of a compact way notation of using this that we'll start taking advantage of, because we'll see this just a ton. Okay, so that's a good piece. And we'll, the reason I'm sort of doing this now is because as we go forward, even though we're going to go back to the sort of undergraduate fluid mechanics books, I'm going to keep up with this notation and sort of I call it advanced math. It's not hard. You just have to get used to the notation. But boy, it's going to make a lot of the stuff that we now do in the remainder of the undergraduate fluids a lot more, from my point of view, a lot easier to understand. You just have to level up your math just a little bit. Okay. And then chapter 5 is just all the basic laws. So I super much appreciate the textbooks that take the time to sort of be complete like this, even though he is writing this for the graduate level environment. It is very complete, from both including a chapter on thermodynamics and then including this chapter here on basic conservation laws, control dynamics, all the stuff that we've already talked about. So good review if you want to go into that. Okay, so the last step is really all of the stuff in chapter 6, and I'm just going to do the first half here. I'm going to save sort of the remainder for another lecture when we come back to it. But the part that I want to introduce here is actually really what is the stress tensor, sort of the viscous stress tensor. And in the undergraduate formulation, we just sort of jump to the straight formulations, and it's okay. I want to take a little bit of time to explain really where most of it is coming from. And so some of it is just saying, if I have a tensor, it's actually like, what are all of the things that it could be? And so the way it's introduced is there could be one coefficient, A1. In fact, I think it's basically saying at first it could be a generic matrix, and then there could be I, J, K, L of based on the gradients K now. So this is where the index notation is super powerful. So you can see this is an applied 3-sum. And this is basically, the most generic way you could write the the stress tensor matrix. Okay, and then we would come with the following assumptions, which is isotropic, which means no preferred direction. Okay, that means that any way you look, there's from that point of view, there's no preferred direction from the fluid, right? There's no even including gravity forces, we may have a way to handle that doesn't necessarily break this just yet. But it's basically saying there's no preferred direction. And then what we want is our stress tensor to not provide any moments. So no torques, generically as it's standing there. Okay? And that actually implies that it has to be symmetric. And so then, starting from here, what we get then is the next level of simplification, which is, okay, so tau of ij, the stress tensor matrix, can be some, now constant, this is not aij, this is some constant times the identity matrix, which we've talked about, plus another constant times, and this is the divergence, del k uk, times the identity matrix, plus a third part, sorry, a3, not b, a3, times the symmetric part, the symmetric derivative, uj. There we go. So that's the symmetric part. Getting back to this symmetric moments. Now, well, we started off with constants. We actually already have names for these. So this one is pressure. In fact, we usually call it minus pressure. This one is lambda, and this one is mu. And so it's sort of the first and second coefficients of viscosity. And you can read into it and dig into what those are, and there's some good examples of trying to understand it. But this is not where we sort of end up, right? With most simple fluids. You can get some complicated fluids. We'll come back and talk about that. But for simple fluids, what we then actually say is the mechanical pressure we would define as 1/3 of the trace of this stress tensor. Okay, that would just be the mechanical portion of it. Okay, so that's sort of definition. So I'll use 3 lines. And so when we then take pressure minus the mechanical pressure, what we're left with is lambda plus 2/3 mu of the divergence, so del k uk. Okay, and that is equal to minus lambda plus 2/3 mu of the material derivative, so 1/rho d rho dt. Okay. And so the Stokes assumption, I'll write that in green. The Stokes assumption is that basically what we call the pressure and the mechanical pressure are one and the same thing. So we want to think of this thermodynamic pressure and mechanical pressure. We're going to call that the same thing. And so the result of that is that lambda is equal to minus 2/3 mu. And so we'll end up just using mu. And that's what when we normally call viscosity, it's normally just mu. And so that will then result in our stress tensor, tau ij, being minus pressure, del ij, minus 2/3 mu, and the divergence, del k uk, plus 2 mu sij. Now you got to be careful on some notation. Some books will define sij without the sort of 1/2 over here. So you got to be careful. So sometimes there's a 2, sometimes there's not. Be careful there. When we are talking about incompressible flows, it's actually divergence free, and so this one will drop out. If it's compressible, it's not. So this form is still true if the fluid is compressible. Okay, so really sort of as we then kind of go forward in fluid mechanics, even back into the undergraduate, we're going to kind of keep this in mind, and really when we cycle back into chapter 6 with Panton, we'll actually have this really good conversation about some weird things that can happen. And it's actually some of the more fun things about fluid mechanics. You can get like strain hardening, and there's all sorts of weird viscosity things that can happen. But for the most part, this is where we're going to sort of land. So take this moment to sort of read chapters 1 through 6 of Panton before we kind of go back into the undergraduate textbook. And so it's because it's really good. It gives you a sort of a better grounding in terms of continuum. You're going to re-attack the thermal, which we've been sort of delivering already. We already did a lot of the index notation. This is simply adding a bit of the stress tensor. Chapter 4, as again, is useful, especially we'll have this sort of material derivative. Chapter 5 should be very familiar. You should almost be able to skim through that now if you've kind of been paying attention and kind of sticking up to the mathematics. So it's good reminder of continuum laws. And then this nice kind of good rigorous definition of the stress tensor is going to be very, very helpful as we then kind of get into some more of these real flows and boundary layers and things like that. So we'll see you next time. Again, if you're liking this book club, please like and subscribe. We'll see you.